auto record, and now I'm going to share this with you. Okay. All right, so now you see my mobile phone. Ah, yes, good. This is what I want. All right. Okay. So I guess for today this will do. I'll try to improve a little bit my system, but for today it should work. All right. So the topic of today it's Bell non-locality. Okay. And so this is quite a special topic, I would say. I have to also admit that it's one of my favorite. It's one of my main areas of research. But still, the story behind all this, Bell's theorem is really quite astonishing. So, of course, the starting point is the notion of entanglement, right, which we discussed already quite a bit in the lecture. And indeed, so by now, I hope you all appreciated the fact that there is something quite astonishing in entanglement, right? So basically, it's the idea. Oh, okay, I leave it there. But okay, you see my hands here. So the point, it's the idea that you. No, sorry, I got confused. You see my hands here. Okay, good. So the idea of Bell is that, of entanglement, is that you have two quantum subsystems, okay? So let me represent it by my two fingers here. And these two subsystems, they form a single physical system, right? So it means no matter how far apart you put them, when you do something on one, like a measurement here in this lab, it immediately has an influence on the other one, right? It collapses the state of the other subsystem. So this is what Einstein called a spooky action at a distance, right? This is what we used, for instance, in teleportation. And so, of course, that is a sort of non-local feature, right, of quantum mechanics. And so this was very unnatural to Einstein, right? So then he said, if quantum mechanics allows for this, well, probably it means that there is some sort of problem with quantum mechanics. So Einstein didn't say quantum mechanics was wrong, but he said maybe it's incomplete, okay? And so the idea could have been that, I make a little drawing here. So in a sense, he thought, okay, we have quantum theory, and this is what we use as a theory to describe physical phenomena. But when we restrict to that theory, there is this sort of non-local effect via the concept of entanglement, right? And so then he thought, but maybe this quantum theory is just like, the tip of the iceberg. It's part of a bigger theory, okay? And this bigger theory is yet unknown to us. However, when you have access to that theory, this spooky action at a distance will disappear because you have a more complete description of the physics, right? Okay. So Einstein put a name on this concept. He said that there should be something like local hidden variables. Okay. So what that means is that there must be a sort of way, according to Einstein's idea, right, to complement quantum mechanics in order to make it a local theory. Okay. So that means that once you have this more fundamental theory, well, then spooky action at a distance goes away, right? And that is a reasonable idea to have, right? It might be that indeed this strange feature of the Hilbert space, where you have these vectors that correspond to entangled state, maybe that is just an effective spooky action that is due to our incomplete knowledge about it. Okay, and so after this 1935 paper of Einstein, Podolsky, and Rosen that put forward this idea, there was a long debate between Einstein and Bohr that is not so interesting, I find personally. The big progress came in 1964, okay, and that was the work of John Bell, who presented his by now famous theorem, okay? So this is the subject of today, Bell's theorem. So that is 1964. Now, this also has a connection to Geneva, actually, because Bell was working at CERN. So he was mainly a particle physicist, but he was also very much interested in foundations. I think he's also famous for contributions in particle physics, but probably this here is by now his most famous contribution. In fact, would he still have been alive in the 90s? Maybe he would have gotten the Nobel Prize for this. But okay, that is just a hypothetical supposition. All right, so Bell said something interesting. He said, I'm a quantum engineer, but on Sundays I have principles. So that meant that, during his free time, he was not doing particle physics, but he was thinking about problems like this one here. All right, so in a nutshell, what is Bell's theorem going to tell us? Well, it will actually tell us that, coming back to this idea of Einstein here, okay, it will give us a way to answer this question that Einstein put forward. So that is, can it be that quantum theory can indeed be complemented into a more general theory that becomes local? Okay, and the answer will be no, this is not possible. Okay, now here you should realize already that this is a very strong and fundamental result, because Bell's theorem is telling us that the predictions of quantum theory are not compatible with any local hidden variable model. Okay, it's not just this particular way of complementing quantum mechanics is not going to work, you see, or maybe that quantum, maybe this theory is not going to work, or maybe that one is not going to work. It's any theory that is local in a sense that we will make precise in a minute. So any such local theory is incompatible with quantum mechanics, okay? And in that sense, experiments that have been done on this idea, demonstrating these effects, they show that nature has indeed something non-local to it, okay? Doesn't say that quantum mechanics is necessarily the correct theory, but it says that there is something like non-locality in nature. All right, any questions so far? No? Can someone say something just to be sure that everything works properly?
Yeah, it's fine.
It's fine. Perfect. Thanks a lot. Oh, good. It's nice to hear a voice every now and then. Good. Okay, so I try to go a little bit in the, let's go to the meat now, a bit more to the details, okay? So here is the thought of experiment that is going to interest us. So it's an experiment where we have a source, okay, represented by this star. And this source prepares some particles, some physical system that are sent to remote laboratories, okay? So here is a laboratory of Alice, okay? And here is a laboratory of Bob. Okay, and the laboratories are sort of represented by these boxes, okay? Now, these boxes, I will actually shadow them like this, because these are black boxes. So it means that I have essentially no idea what's going on in these boxes, okay? All right. Now, what is going to happen? Well, what is going to happen is that each physicist here, Alice and Bob, okay, they can actually challenge their physical devices here, okay? They can ask a question, okay? And to this question, there will be an answer, okay, which I denote like this. So a concrete example could be that Alice chooses to make a certain type of measurement, okay? And then there will be an outcome of this measurement that will be recorded, okay? But you could also think differently of this scenario. You could think that Alice and Bob are professors, okay? And instead of having two particles here, we have two students, okay? And the point is that the students will receive a question, okay, which corresponds to the choice of measurement, if you want. And to that question, they will have to provide an answer, okay? So of course, I have the same thing here. Okay, so let's go on a little bit with this idea of the professors asking question to the students. In this, you see this sort of bipartite configuration, right? So first of all, let's imagine the case where the professors run this experiment. Okay, so the point will be that we imagine doing this in a sequence, that in each round we have students going to the professors and then answering the question they receive. And after, let's say, 1,000 rounds or something like this, the professors come together and they check that whenever they asked the same question, okay, the students gave the same answer, okay? So that is quite realistic situation. And so now, comes the question of how did this work, right? Okay, so the first explanation, okay, because let's assume that the professors are a bit paranoiac somehow. So they imagine that, in fact, maybe the students gave the same answer because the students sort of communicated, okay? So that means whenever this student here went into the room, okay, he received the question, he knew the answer, so he will give the correct answer, but then he will also communicate the answer to his colleague here, right? So it might be that you have something like a communication from A's lab to B's lab, okay, or from that office to this office. So of course, professors want to prohibit this, right? Because they don't want the students to cheat. So here is a very simple way to prevent it. Well, you put these two events here of A giving a question and receiving an answer, and the same on B. You put them in space-like separation. So you essentially put them very far apart. And so then you can rule out this cheating strategy via communication because, the two events are space-like separated. So for now, we will assume that, nothing goes faster than light. Later, one can maybe challenge this idea, but it will bring us too far. So if we have this space-like separation between A and B, and if we still see correlations between the results, between the answers giving the questions, right? Well, then we have to conclude that it was not a communication from A to B that could explain or mediate these correlations. It must be something else. Now, if it's something else, what can it be? Well, it's pretty obvious, I guess, at this point. The students, you see, they actually came from the same place, the source here, okay? So it means that they worked together, right? And they are good students, so in fact, they they learn the courses well. So the fact that they give the right answer for each question means that they are just good students, and they are good students, so they correlated themselves in a sense, and this explains why you see this this correlated behavior. Okay, so here is our first sort of important point. So the fact is that correlations can be mediated in two different ways. So the first way is via communication, or two, by what we are going to call a common cause. Okay, so communication is a signal going from A to B. A common cause is the fact that the two students here were, sort of prepared. I mean, prepared makes more sense when you're going to talk about particles, but they originate from the same source. Okay, so that explains why they can be, sort of programmed in the same manner. Okay. Now, why is this interesting quantum mechanically? Well, it's interesting quantum mechanically because we are going to show the following thing. We are going to imagine now an experiment like this one here with quantum particles. So this source here is going to prepare entangled photons, for instance. Okay, and each of these photons will be measured here locally. And so this will give rise to some statistics. So like before, this is an experiment that we are going to repeat many, many times. And there are different possible questions which correspond to measurements made in different bases. For instance, one measurement could be the Z basis, another measurement could be the X basis. And so that's why we need many, many rounds of this experiment in order to get some statistics. And the statistics will be the joint probability distribution of the results given the question. Okay, we will make that formal in a minute. Now, remember, our goal is to address the question of whether the predictions of quantum mechanics for such an experiment, which we can easily, by the way, calculate via the Born rule, okay? We will do it in a minute. So whether the predictions of this experiment are compatible with any theory that is local, okay? So if we go back to our model here, what it means is that, and we are going to prove that this is not possible, right? Now, the point is the following. So first, we have to rule out, so we have to rule out each of these two explanations, right? Because these would be explanations for correlations that you observe in some experiment like this one. And if you can rule out each of these two, you have to conclude that there is something very special about quantum theory, okay? So first, how can we rule out a communication? Well, communication we can rule out, okay, because we put a space-like separation. This we argued already. Okay. Now comes the question, can we rule out a common cause? Because, of course, as in my example before with the students, well, it makes sense that you can observe correlations between A and B because these are mediated by a common cause, right? Because the particles originate from the same source. Now, turns out that this we can also rule out, and this is done via Bell's inequality. Okay, so what is this going to be? Well, it will be a mathematical proof, which is pretty simple, that there is a limit to the strength of correlations that you can observe between A and B whenever these correlations are mediated by a common cause that is given by some local information, okay? So that means that instead of having students here, you imagine having computers or whatever piece of classical information, you know. But again, it can be of any complexity, right? You imagine, I think the example of computers is good. You send a computer to Alice, another computer to Bob, of unlimited computational power. And so with a program that can be arbitrarily complicated. And so that is the type of models that we are going to test here, okay? And so Bell's inequality proves that no matter how powerful your computers are here, if they still mediate classical information, then they are incompatible, or they are not able to reproduce the correlations that you see in a quantum experiment, okay? So the quantum correlations are strictly stronger than what you could ever possibly do via computers. Okay, so again, it's a strong result, right? Because it holds for absolutely any, you know, possible model where you have classical information sent to A and to B. All right, any questions so far? Okay, good. So then I continue. So here is how we are going to test our idea, right? So I don't come back to the case of classical communication. This is a simple point of separating enough the particles in space, right? Now here is the more tricky part. Okay, so how do we prove that there is indeed a limit to the strength of correlations that you can see with any model that is local? Okay, so here is how we do it. We do it via some game. So this is Bell's game. Okay. So this is a game where I imagine that I have here two possible questions, which I denote x equal 0 or x equal 1. And here I also have two possible questions. So again, questions are like choice of measurements, or question asked by the professors to the student. You can think of it as you want. And so what we are going then to say is that the answer to these questions, this will also be binary, okay? And here, this is going to be +1 or -1. Sorry, I try to write well. Okay, and so just to make my notation clear, what I'm going to do is that I will write A index X for my answer here, right? So you see, so I have an answer for question 0 and an answer for question 1. Again, in each round of this game, there is only one question that is asked, okay? But this is a convenient notation to represent the answer for each question. So on Bob's side, I do the same, and I put an index Y here, okay? Now here is the game I would like you to look at. So it's, I mean, at the moment I just specified how many questions and how many answers, but I didn't give you the rules of the game. So here are the rules of the game. So it will be convenient to represent it graphically like this. Okay, so I write my 4 variables. Okay, so these are the answers for the 2 questions of Alice, and here are the answers for the 2 questions of Bob. Okay, so here is now the set of rules that are going to give points to the, to the students or to the particles. So whenever it was question A0 that was asked on Alice's side and question B0 on Bob, I will demand that the outputs here of these measurements are correlated. So green here means correlated. Okay, so what does correlated mean? Well, it means that they are the same, right? So it means that the outputs could be plus plus or minus minus. Okay, so let me emphasize that I'm not interested in whether A0 is plus or minus, right? I'm only interested in the relation between A0 and B0, okay? Good. Now, here are the rest of the rules of the game. So whenever you have question 0 on Alice and question 1 on Bob, well, we are going to demand correlated behavior as well. For A1, B0, same thing. Okay. And here comes the tricky part of the game, is that whenever we have question A1 and B1, well, we would like to have, okay, maybe I can draw it like this, okay? So here I would like to have anti-correlated behavior. Okay, sorry, I hope this is readable. So anti-correlated means different. Okay, so it should be a plus minus or a minus plus. Okay, and that's it. Okay, so this is the definition of the game I want to look at. So it seems like a simple game, perhaps a silly game. That's possible. Nevertheless, you will see that this game is sort of clever enough in order to capture something about the limits of correlations in this type of experiments. Okay. So I gave you the rules of the game. Now, how do I give points? How do I give a score? Well, I give a score whenever, you know, any of these relations here is satisfied. Okay. So again, how does it go? It's a game that we play statistically, right? So we have, let's say, 10,000 rounds of this game. In each round, one question is asked on Alice's side, and an answer is given. And in each round, one question is asked on Bob's side, and the answer is given. Okay? And these questions, they are chosen at random. Okay? This is very important. So for the source here, or for the students, they know that the question will either be 0 or 1, but in each specific round, there is no way for them to tell whether the question will be 0 or 1. Okay? So in a sense, we have to be prepared for both questions. Is there a question? I heard some noise. No, you all good? Okay, so let's continue. Okay, so my claim is that this game here is non-trivial. So it means that no matter what strategy you use, you are never going to be able to get the maximal score. So in a sense, this means that no matter which strategy you use, you will never get all of these relations correctly. Okay? So I think the best way to convince you about this is to try. So let's try to play the game, okay? So play the game means what? It means that you have to imagine that you are now the students, okay, that are going to play the game. So one of you will go to this room here, receive question that is either 0 or 1, and then you have to give an answer, +1, -1. And the other one goes to this other room, receive an unknown question, 0 or 1, and then give an answer, okay? But the point is, you can use whatever strategy you want before going to the rooms, but once you're in the room, of course, you cannot tell the other one what question you got, okay? So that's the point. Okay, so let's see how we do this. We try to play the game, okay? So we have to start somewhere, and we are going to say that that A0 here will be fixed to a value of +1, okay? We could also have chosen -1, of course, but you see, somehow we need to start somewhere. Now, what should we do for B0? Well, clearly, if we set a +1 here, B0 has to be +1 as well, okay? Because we want A0 and B0 to be correlated, okay? Now, what should we do for A1, okay? Now, remember, the point is when the student here or the particle gets question 1, okay, he has no idea which question was received on that side. So it might very well be the case that the question was B0, okay? So that is, in fact, in half of the cases, that will be what happens. So therefore, we have to give an answer for A1 that takes into account what we did already here for B0, right? So that means that we also have to give the result +1 here, okay? Then we satisfy this green relation. Now, finally, what should we do for B1? Well, because of the same reasoning here, when B got question y = 1, it may very well be the case that Alice chose question 0, okay? So if we want to satisfy this green line here, well, we better also output +1. And now you see we are done. We have decided our strategy, and you see that we have a problem, right? Because for the final relation here, we wanted anti-correlated results, but we have correlated results, okay? So the score that we managed to achieve here, it's not so bad, right? We satisfy this green line, and that green line, but this one we got wrong, okay? So our score here, let me write it like this. So our score is equal to 3 out of 4, okay? And now the content of Bell's inequality is in fact the following. It is telling us that for any possible strategy that you can imagine here, okay, based on local variables, there is no way for you to make a larger score than 3 out of 4, okay? Now, can we justify this intuitively from our discussion here? Well, I guess my example was clear, right? That it has to satisfy this limit. You can also convince yourself that if I had started, you see, from -1 here, or if I had started from B0 or from B1, I will always get some limitation. And the reason is that you see this setup here is like a frustrated chain. Okay, there is a frustration in this thing that you cannot set 4 values to these variables that satisfy all the relations here. Okay. All right, now the content of Bell's theorem is this, right? So this limit on the score. And in fact, so this is true really for any possible strategy that you can imagine here. And in particular, you see here we have strategies which are deterministic in the sense that I said here, okay, for A0, the result is +1, or I could have said it's -1. But of course, in general, I could also say sometimes it's +1 and sometimes it's -1. And depending on that, here I could also have something different. Okay, so that is going to be a probabilistic strategy, but never mind. All of these strategies have to fulfill this. Okay, so this is true for any local strategy. Okay. All right. Now this is a very simple form of Bell's inequality, but somehow I guess this is it's the most intuitive way. Okay, at least from my point of view, from this little game here. I guess. Well, I hope that most of you are already convinced that what I say here is correct. In fact, maybe most of you are convinced that this is a total triviality. And maybe, in a sense, you're right. This is extremely basic, and it seems pretty obvious that this inequality has to hold. Now, what is really amazing here is that this inequality here does not hold in quantum mechanics. So you can imagine a quantum experiment where you use some entangled state and some measurements here that will achieve a score that is strictly bigger than this limit here, okay? And that's why we have Bell's theorem. So if you want, Bell's theorem goes in two parts. The first part is to prove this inequality here, okay? So this is Bell's inequality. So first we prove that there is a limit on any correlations that can arise from classical variables, so from a common cause, no matter how complicated they are. And the second part of Bell's theorem is to show that this limit that we have established formally is broken in quantum mechanics. And we will show this by a specific example, okay? All right. Any questions so far? No? You're all happy? Good. Okay. So then I continue. Let me see how to do this, because I want to reuse some of this here. Okay, I think this works not too bad. Now I would like to give you a formal proof of this, okay? Because what I discussed here, this is somehow intuitive, it's simple, but I want to prove this rigorously, okay? And here is how we are going to do it. So my score, I will write it now as a mathematical function, okay? So I just use S, and S will be defined in terms of these variables here. So S, I claim, is the following thing. It's A0 times B0 okay. So to be more precise, what I claim is that this function here, okay, or this value, if you want, this expression, it corresponds to this score. In fact, it is the same up to the denominator here, okay? So S is actually 4 times the score as it is written here. So let's see why that is the case. You see, the first term here, A0, B0, it corresponds to this part of the game, okay, the first line here. Now, when do I gain a point? I gain a point when A0, B0 are correlated. Okay, so whenever it's plus, plus, or minus, minus, in which case the product here of the two will be equal to +1, okay? If they are different, this would be equal to -1, but I want to maximize my score, okay? And that will correspond exactly to doing this here. Okay, so correlation means that the product of the variables is equal to 1. So whenever I would like to have correlations, I put a sign plus in front. So here I want correlation, here I also want correlations, and here as well. And the final bit here is when I would like to have anti-correlations, well then, you see, I just put a minus in front, okay? And the point is that whenever A1 is different from B1, the product is -1, and so the minus then cancels this one, and I have again a positive contribution. All right, so that's the idea, okay? So I hope that is clear. Now I will just do the following thing. I will do some highly sophisticated algebra, as you can see. I will just pull out A0 and A1. Okay? So really nothing to worry about. Now, this form is nice because it allows me to see immediately that this thing is never bigger than 2. Okay, and so why is that? Well, the point is that you see B0 and B1 can either be the same or they can be different. So if they are the same, well, then this term here can be +2 or -2, but then this one is 0, right? So this one here is +2, -2, this is +1, -1, so obviously this thing cannot be bigger than 2, okay? And so that was the case when B0 was equal to B1. If B0 is different than B1, okay, then this thing is equal to 2 or -2, and that thing is equal to 0, okay? And of course, because my game is binary, right, the results are either +1 or -1, there is no other possibility. Well, I have already explored all cases, right? So this inequality here is established, okay? Now, the point is that, again, here, when I did this reasoning, I said, okay, B0 is equal to B1. So I'm sort of saying that the outputs, these values are chosen deterministically, right? Which may not be the case. It might be probabilistic. However, for a specific strategy, right, these things will be deterministic. So what I need to do now is I need to incorporate this element. Okay, so I will add a variable lambda here, and this lambda, this will denote my choice of strategy. Okay? So now what I claim is that for any strategy that I choose, that thing will be no larger than 2. Okay? And without loss of generality, I can say that my strategy here is deterministic. Okay, that these results are given deterministically. Now, okay, we need to do one more step, namely the fact that we need to make a connection to the statistics that we see in our experiment. Okay, because the idea, let me come back a minute to my original experiment here. So you see, in my experiment, I have a source which I am testing via these questions and answers here. But again, I have no idea what is prepared here in this source, right? I have no idea, for instance, what is the strategy chosen by students. And if I don't know what is the strategy chosen by students, then it is not okay that I have an expression that depends on the choice of strategy, okay? So I want to get rid of this variable here, okay? Because what I observe when I do this experiment, I observe the mean value, okay? I observe the mean value over this parameter S of lambda here. And it's the mean value because I will have to average over the strategies because I don't know what strategy has been taken, okay? So let me do that. I do it as follows. So I will have to calculate now something that I call S, that no longer depends on lambda. And this is going to be the integral over d lambda. So I integrate over the space of strategies, right? Again, I'm not enumerating these strategies, could be whatever, it's just whatever strategy is possible. And then for each of these strategies, there will be a probability. Okay, so P of lambda, this denotes the probability of choosing strategy lambda. Okay, so of course I have that P of lambda is non-negative, and the sum or the integral over lambda of P lambda is equal to 1. Okay, this is a valid probability distribution. But it's an unspecified probability distribution. Okay, I don't know what is this. I don't know what are the strategies, and I don't know with which probability they are chosen. Okay, and now, so how do I go to S, okay, well, I have to put here S of lambda, right? So I have to average the score here over all possible strategies. And again, I don't know what is the distribution of strategies, but what I'm going to say now is true for all distribution. And what I'm going to say is that this quantity here, okay, this is upper bounded by 2 again. Okay, so let me just justify this. Well, this is justified because I have a function here that is never bigger than 2. So if I average it, okay, then the average cannot be higher than 2. Okay, so it's pretty trivial. All right, so maybe let me make one more statement here, and then we do possibly a small break. So now I would like to connect this score to something that I can observe in my experiment. I guess it's already intuitive that this thing corresponds to the score, okay? So of course I can observe it, but it would be nice to just make it a little bit clearer. So you see S is the average of this quantity here, okay? And so in this equation, I don't write a dependency on lambda, on all of these things, okay? But I could, okay? And so then when I would like to rewrite S depending on these variables, I can just pass the averaging over the strategies to each term here, right? Because this is linear. So when I do that, I get that S is given by the following thing. So it's the average of the product A0, B0 plus the average of A0, B1 plus the average of A1, B0 minus the average of A1, B1. Okay, whoops. All right. And now you see this is a form of S that is useful because if I do an experiment, okay, so if I come back to my little experiment here, well, let me do it like this. So you see, I do my experiment, I do 10,000 or 100,000 rounds. In each round, I choose an X randomly, and here I choose a Y randomly, and then I write what are the results. And I repeat this 10,000 or 100,000 times, so I can get pretty good statistics, and then I can estimate each of these 4 expectation values. Okay, and so when I do that, I can calculate my score S, and then I can check it with respect to Bell's inequality. So if I see a score of 2, I will conclude that there is nothing strange here, right? Because I can perfectly explain how this was created. For instance, via this black strategy here that we considered before. However, if I find a score that is larger than 2, okay, then I have to start scratching my head because here I gave you an almost trivial proof that this S here has to be upper bounded by 2, right? And so, for instance, in quantum mechanics, we will see that S can go up to 2 times root 2, which is about 2.8, okay? So quite a bit larger than this limit that we have proven here, okay? So let's finish this. So Bell's inequality is telling us the following thing. So it's telling us that this quantity S is no bigger than 2. So this is Bell's inequality. And in fact, so to be historically correct, this is in fact not the inequality that was derived by Bell in '64. Bell derives something a little bit more complicated that has some disadvantages. But this is the form derived by 4 gentlemen called Clauser, Horn, Shimoni, and Holt. Okay, and that was done in 1969. So in fact, this is what we call the CH-SH inequality. Okay. All right. So I need to drink a glass of water, and I guess some of you as well. So I suggest we stop for 5 minutes or so, and we reconvene in a bit. And so in the meantime, please think of any questions and so on, and so that maybe we can start the second hour with some discussion on some question. Okay, very good. Okay, so yeah, sorry, I didn't record the question. My mistake. I will do it next time. Let me come back with my little installation here. Okay, yes, I have to do this again. Up. This works really nicely. Okay, we're back. Good. Okay, so that was my first bit here. So now we are going to go to the quantum part, okay? So the quantum part is what? Well, it's an experiment, a specific quantum experiment, whereby, you know, we're just going to do standard quantum mechanical computations, as you know how to do them, and with that we will get the score, okay? All right, so do I want to, maybe I do it again, okay? So this is now my quantum experiment, okay? So it looks very similar, of course, because the general setup is the same. I draw it again. Okay, so now what is new in my quantum experiment? Well, what is new is that I can use a quantum state, okay? So this is an entangled state now between the two. In fact, okay, I wrote phi, but I would prefer, yeah, I cannot erase this, but okay. So I will do like this. So my state here, in fact, so sorry for the change of notation, but so I would like to have a state that is the singlet state. Okay, so it's one of the 4 Bell states, and it's 1 over root 2, 0, 1, minus 1, 0. Okay? So now I think I can just skip it. We will come back to this in a minute. So this is my quantum experiment. I told you what is the entangled state that Alice and Bob are going to use. Sorry, also to be consistent, I should put capitals here. So this is AX, BY. Okay. Now, in order to get the statistics for these measurements here, or define what these questions and answers are, I need to tell you what are the measurements that are performed inside these labs here, right? So these measurements, well, you see, Alice and Bob each have 1 qubit. So unsurprisingly, these are just single qubit measurements. And so here I specified the state, okay, that is the first ingredient. And now I will specify the measurements. And so the measurements are like this. So I will, I can immediately use a notation of observable here, because you see again the results here are +1, -1. So you see that fits very well to observables like the Pauli matrices, for instance. And so I will choose A0 to be sigma Z, okay? And I will choose A1 to be sigma X, okay? So why not? Huh? That is it sounds like a nice choice, because you see sigma Z and sigma X they're incompatible measurements, right? They don't commute. So indeed, I have something really quantum mechanical here, right? Now on Bob, let me write them down. So the measurements are going to be sigma X minus sigma Z. So this needs to be normalized, right? So that's why I have this factor 1/√2. But you can check that this is a +1, -1 eigenvalued observable. And then I have B1, which is sigma, sorry, I missed, there has to be a minus here as well, and this is a sigma X minus a sigma Z. Okay, like this it's correct, okay? Okay, so now I claim that with these ingredients, so my entangled state and this choice of 4 local measurements, 2 on Alice, 2 on Bob, so I claim that with this, I achieve a score that is better than 2, okay, for my CHSH gain that we discussed before. All right, so this we have to verify, right? We have to calculate. So remember that when I want to calculate S, I'm going to need to evaluate objects of this form. Okay, I will need to have the expectation value of some variable representing the output here and some variable representing the output there. Now, luckily for me, this, in fact, you see, corresponds exactly to the expectation value of these observables, actually, right? I will write it. This is going to be given by psi minus. So, yeah, there is a little abuse of notation here, but I hope this will be clear. So here I'm just using the Born rule, right, in order to evaluate these expectations values that I'm going to need. Okay, so here, if you want, these are the variables for these outputs here. Okay, so these are the corresponds to the 4 terms that arise in my score. And here is how I calculate them quantum mechanically. I put the operator in the middle, so it's a tensor product of some Pauli observable for A, some other Pauli observable for B, and then I sandwich this with psi minus, which is my state, right? So this is really just applying the Born rule. Now I need to tell you something about this expectation value, which in fact is relatively simple. And it's simple because I have a singlet state here, okay? So the reason why it's simple is that the singlet state is the totally antisymmetric state. So imagine that you write now your observable in the following form. Okay, so you see this here corresponds to the observable of Alice, okay? But by this thing here, maybe let me write it explicitly. I'm using here already a Bloch sphere representation of my observable, okay? So what I mean by this is that this is AX sigma X plus plus AY sigma Y plus AZ sigma Z. Sorry, I hope this is readable. But you see, it's a bit of a convenient notation where I write plus minus one eigenvalued operator like this. So it's a vector. This is the Bloch vector of the measurement on the Bloch sphere, okay? And that now is multiplied by a vector of the 3 Pauli matrices, okay? So a bit of abuse of notation, but it's convenient. And now you see, if I have everything here, if I have taken the time to write everything with the Bloch vectors, is that this thing is extremely simple. This is just minus the scalar product of the 2 Bloch vectors. Okay, and so remember the singlet state is the fully antisymmetric state. So essentially it means that in whatever basis it's a state that looks like this or like this, okay? It's fully antisymmetric. And so this is true, yeah, sorry. It's true in any basis. And so you see that this is the case, right? If A is equal to B, and no matter what this vector is, then the expectation value here is always minus 1, okay? So the results are always opposite. Okay, so that is this property of being fully antisymmetric. I think you had it in one of the tutorials, so it should be okay. Good. Okay, so now with this, I can go on to calculate S. Okay, so S is what? It's A0, B0 plus A0, B1. Let me do it like this, plus A1, B0 minus A1, B1. Okay? Good. So now I just plug all of these things here, okay, use this formula with the Bloch vectors, which is very convenient, and then I will calculate my score. So let's do it. So let me start with this guy here, okay? Well, you see, it will be, in fact, useful to represent now my measurements in terms of Bloch sphere, okay? So I can do that. Let me do it here, maybe. So let me do like this. In fact, it will be enough to use a circle. Okay, so this is like the equator of the sphere. And you see, because all my measurements, they involve only Z and X. Okay, there is no Y in this. So I can represent everything on a disk. And so now, where are my measurements? Well, A0 is Z. So this is A0. Okay, you see I follow this notation here. Okay, so now small a vector is the Bloch sphere vector of the measurement capital A0. Okay, so then the X is then here. Okay, so this is A1. Okay, and maybe let me draw Bob in red. So Bob's measurements are so X minus Z, oops, X minus Z is here. So you see, this is intermediate between X and minus Z. So minus Z would be here, X is there. So indeed, B1 is here. And then B0 is in fact here. Okay, B0 is intermediate between minus Z, which is here, and minus X, which is there. So it's here in the middle. Okay, so now I have my 4 Bloch vectors, and now I can just compute, right? So I can compute what is A0, B0. Well, that should be minus the scalar product between A0 and B0, okay? If you see, if you wanted, yeah, no, okay, let me not put an X, it will complicate, but okay, I guess it's clear, no? Here I have these two. If I write it like this, it's the minus the scalar product of the associated Bloch vectors. So this is A0, B0, okay? So what is the scalar product? Well, you see they are sort of anti, I mean, if they would be anti-aligned, the scalar product would be -1. They are more like this, okay? So in fact, maybe I just tell you the answer. The answer is that the scalar product is -1 over √2. Okay, sorry, I hope you can read this. This is 1 over √2. But there is a minus sign here, right? So it is the scalar product itself that is -1 over √2, but with the minus sign in front, I get a +1 over √2. Okay? Now, what is A0B1? Well, A0B1 is in fact the same. It is also 1 over √2. Why? Well, if you look this picture, it's pretty obvious. The scalar product between this pair is the same as that pair. Okay. Now let's go to the next. This is also 1 over √2 because this is between A1 and B0. Okay, so you see it's still the same angle. And now the last one, well, the last one, it is different. This is -1 over √2. And it's -1 over √2 because you see these two, they are close now. A1, B1. So the scalar product here is 1 over √2. Okay, and then I have the minus sign here. Okay, so this expectation value is -1 over √2. Okay, so now I put everything together, and what do I get? Well, I have 4 times 1 over √2. Okay, because this is a 1 over √2, another one, and here I have a minus and a minus. Okay, so I have another positive contribution. And so if I divide 4 by √2, well, I get 2 times √2. And this is about 2.8. Is it 2.8? I guess it's 2.82. Okay, and of course, 2.82, well, this is much bigger than 2. Okay. So the conclusion is that this particular quantum experiment leads to statistics that violate Bell's CHSH inequality. Okay? Because, well, you all remember from before, right, that in principle, in these type of experiments, if you have classical information, no matter how complex this is, S can never be bigger than 2. Okay? And here, I showed you a simple quantum experiment, okay, of course a well-chosen one, but it's pretty simple. I mean, it's just 2 qubits. We used Born's rule and a bit of geometry on the Bloch sphere here, and we calculate that the score is 2.8, so much bigger than 2. Okay, and this effect here, this is what we call quantum non-locality. Okay, and so quantum non-locality is the fact that in quantum experiment, we can have, in quantum theory, we can have experiments like this one here, and these experiments lead to statistics that are not compatible with any local theory, okay? What local theory here means is the fact that instead of sending a quantum state here, this source would have to send classical information on both sides. But these classical informations is what we wanted following Einstein's idea, because these local variables or this local information should, you know, be the information that removes the spooky action at a distance, right? And so what this here shows as a sort of second part of Bell's theorem is that quantum mechanics is not compatible with any theory that uses local variables to mediate correlations. All right. There is some question. Let me see. So unfortunately, when I share, okay, I can see it here. Good. Okay, so someone is confused with the signs of the scalar product. So maybe let me just go through it again, because there are many scalar products, so I don't know exactly, but I hope you're all happy with this formula here, which is the correlations for the singlet state. So it has this minus the scalar product, so it's this completely anti-symmetric property. And now let me do this example again here. So how I calculate this expectation value? Well, I said this is for A0, B0. So this corresponds to these two Bloch vectors. Okay. Now, these two Bloch vectors, well, they have a scalar product. You see that it's clearly negative, right? Because these two vectors, they are closer to being anti-aligned than being aligned, right? So, so you see, if the red one was here on the south pole, it would be, the scalar product would be -1. If it was here, the scalar product would be 0, okay? But in fact, because it's sort of intermediate, well, you can calculate by writing explicitly the vectors, but you will see that the scalar product is -1/√2. Okay, so this part here is -1/√2, and then you have another minus sign in front because the singlet is anti-symmetrical. So that's why we get a 1/√2. Okay, you got it. Perfect. Okay, so I hope everyone get it. Are there any other questions? Yeah. Again, please.
Actually, I have one.
You have one. Perfect. Yeah.
Yeah. So you earlier you parameterized different strategies with lambda.
Yes.
Here you have just one strategy, right?
Yes.
So you have a discrete example where P of lambda is just 1, and you have just one.
Yes. Mm-hmm. Yes, you're right. So I could also use a quantum strategy that is probabilistic, where, for instance, I use either this state or another state. Okay, but you see, the reason why I didn't do that is because here I have a very different goal than before, right? Because before I wanted to prove to you that there is a limit to the correlations for any possible classical experiment.
So you just want to find a counterexample.
Here I just want to find a counterexample, exactly.
Nice.
Okay, it's a good question, yes. Mm-hmm. So you see the two parts, they go in sort of opposite spirits, yeah. All right, so everything clear on that? Okay, very good. So let's move on. So maybe now let me go back to the idea of locality. So, and maybe let's write it a little bit more formally. So this is the idea of, so what is exactly, because here you see we say quantum mechanics is not compatible with local theories. So what do we exactly mean by local theories, okay? So there is this intuition that in our experiment there is classical information flowing out of the source, but can we make this more precise, okay? So here is how it goes. So we are going to say that the information that flows out from the source, it's represented by lambda. Okay, so that was our variable for the strategy. But again, think that this is any possible classical variable, right? Encoding information that is as complex as you wish. Okay, so this information flows to the boxes. Okay, and these physicists here, they make measurements. Okay. Oh, all right. Maybe I use capital again here. Okay. So they make this experiment where they choose something to measure represented by variable x and y here, and some results A and B. And now these things no longer need to be binary, right? Could be anything. Could even be something continuous, right? This could be a measurement of the position, and then here you would have a real number as the result, okay? Now, so here is the idea of locality. So the idea of locality is that the statistics that you observe, the statistics that you observe in your experiment, which is given by the following thing, okay? So this thing is the statistics. So these statistics, you can write as follows. Well, this is the statistics that is observed. So it means that for this one, you have no idea how it was created, okay? But if you have the promise that it came from some local variables, you know that this must correspond to the average over some variable lambda of some distribution PAB XY conditioned on lambda. Okay? So here you see, so for each lambda there is some statistics, and the observed statistics on which because we have no information about what is lambda, is observed by taking this average. Okay? Now, here comes the idea of locality. So the idea of locality says that this term here, okay, this is equal to the following thing. It's equal to the product of PA x lambda times PB y lambda, okay? And here I write P, but of course these things don't need to be the same function, so maybe let me write a PA and a PB, okay? So this is the idea of Bell locality, okay? So what does it mean? Well, you see, it means that if I look only at the probability of the output A here, right? This output A depends on X, okay, obviously on the choice of question, and it depends on the variable lambda, right? That is entering the box here. But because of the space-like separation, A cannot depend on Y, okay? So that's why here there is no dependency on Y. So that captures the idea that A is produced locally, okay, here. So it can depend on X and on lambda, but not on the distant choice of measurement Y, okay? And similarly, on Bob's side, you see the output B is chosen or depends on Y, and it depends on lambda, but it does not depend on X. Okay, so that is the idea of locality properly formalized. Okay? And so with this in mind, well, now we can make a general statement here, which is the following. So any probability distribution PAB given XY, so any observed statistics. Okay, here it's a little bit of an abuse of notation, right? Because this is it's a joint conditional probability distribution, but okay, still. So any, if you want, any observed statistics that admits a description in terms of local variables. So that means that it satisfies this equation here, okay, with this constraint here inside, okay. So any such distribution necessarily satisfies Bell's inequality. Okay. So you see the Bell's inequality as we derived it before, like the CHSH inequality, has to be satisfied for every probability distribution that admits a description like this. Okay. So you see there is something interesting here in the sense that even if I do a quantum experiment, right? So imagine I do a quantum experiment, but I don't do the one I described before. I do a sort of bad one where I measure not quite the right things, okay? Then this leads me to a statistics, to some observed data here, this probability distribution. Now, even though I did not, create this distribution via local variables, okay? But just if this distribution can be written in this form, right, then it will have to satisfy Bell's inequality. Okay? So you see, this idea of Bell theorem is to discuss the property of a joint probability distribution. Okay? And what I'm interested in is, does it admit a local form, right? So can I explain it in terms of local variables? If you find an explicit decomposition of this form here, then the answer is yes, okay? Then your experiment does not contain any non-locality. Your experiment can be explained in terms of local variables. You may not know what these are, okay? But it can be explained. Now, you see this statement is important here because of the converse. So if you see data here, observe statistics that does not satisfy Bell's inequality, so data that leads to Bell inequality violation, then it follows that it cannot be written like this, okay? So it means that you can never explain your observed statistics in terms of, these local variables, giving rise to the correlations that you see. Okay. So that's the more formal way to see it. So again, I maybe I insist once more on this idea. So you see what we call locality and non-locality here has to do about the strength of correlations with respect to this type of definition of locality, right? So in other fields, sometimes locality is used in a slightly different way. For instance, in field theories, sometimes locality refers to what we call no signaling. Okay, so to the fact that the choice of measurement here cannot influence the statistics here. Okay, so that is no signaling because it prevents action at a distance, right? So it prevents that A could use this effect here to signal instantaneously to Bob. Okay, so that is what we call no signaling. But when no signaling is satisfied, as for instance in quantum mechanics, it is still possible to see correlations that are stronger than any of those of a local theory. Okay, so there is a distinction between local, non-local, and all that is yet non-signaling. Okay, so keep that in mind. All right, so now let me continue. Let me just discuss very briefly something called Cyrelson's bound. You can see more on it in the note. And here the question is, how non-local is quantum theory? Or in other words, how strong are, let's put it like this, it's better. How strong can quantum correlations be? Okay. I could even have written how strong can quantum non-local correlations be? So that's an interesting question. And in fact, so this gentleman here, Cyrelson, who died very recently, proved some very elegant result. So his result goes back to the CHSH inequality, right? So remember that the CHSH inequality says that S is no bigger than 2. This is for local theories. Okay, so that is, if you want, that is Bell's inequality. Okay. Now what Cyrelson proved is that in quantum mechanics, S is no bigger than 2√2. Okay, so this is for quantum mechanics. And this is Cyrelson's inequality. So if you want, it's the analog of a Bell inequality, but for quantum mechanics. Okay, so so it's an interesting result, you see, because before we had a look at a specific quantum experiment, and this quantum experiment, you remember, it gave us 2√2. But of course, as you know, someone noted before, this is just one particular experiment. So maybe it could be that in quantum mechanics there are better experiments, right? Maybe more complicated, involving different types of measurements or entangled states of higher dimensions. There are many possibilities, right? However, Cyrelson proved that this is not true. Okay, in fact, so if you have 2√2, this is in fact the maximal value that you can get in quantum mechanics. And this raises also an interesting fundamental question, which is, why not more than 2√2? So fundamental question, why not 4, for instance? Maybe why not S equal 4? Okay, because you see the game I described, this CHSH game. Well, okay. It's a relatively simple thing. I hope I all convinced you that there is this limit for local theories or for classical correlations. Now, in principle, let me show it to you again. Here, so here is my game again. So you see my game, it has 4 terms. So obviously each one is bounded by 1 or -1, but of course the algebraic maximum of this function is 4, right? If this is +1, +1, +1, -1, I get a 4. So why can it not be that quantum mechanics goes beyond 2√2, right? That sounds, it's astonishing, right? Why is there this limit? And so, in fact, this has motivated many people, in fact, including myself, to think about what would happen in a physical world where you would have, for instance, S = 4. Okay, and the reason to think about this is that, you know, it goes back to the very first lecture, namely to the fact that the axioms of quantum mechanics are relatively strange, right? So the axioms of quantum mechanics, for instance, state are vectors in a Hilbert space. They seem to fall out of the sky, right? They have no clear physical meaning. It's more about mathematics. But when you use them, you get, you know, very powerful theory. And so some people have thought, okay, maybe we can actually reformulate quantum mechanics. So maybe we can derive quantum mechanics from different axioms that would be more physical. Okay, and so for instance, you see one axiom that would look quite physical in the context of this game would be to say that you are not allowed to signal, right? So you can play this game here. Maybe let me show it here. So you can play this CHSH game between A and B, but you have the limitation that you should not be able to signal from A to B, right? So by choosing X, you cannot instantaneously influence the statistics here, and vice versa for Y and A. So intuitively, it could be the case that if you impose this restriction, well, then you have a non-trivial limit on what S can be, okay? And it would have been absolutely beautiful if that limit had been 2√2, because then it would have been a good idea to use the concept of no signaling as an axiom of quantum mechanics. However, that is not possible. And the reason is that you can show that even with some physical theory that satisfies no signaling, you can get S = 4. Okay? So if we have time in the end of the course, we will have a lecture on these sort of more fundamental questions. But I just wanted to mention it here. Okay? All right, so it's almost 2:30. So what I would like to do now, so I won't give you a proof of this. You can check it. It's in the lecture notes. It has to do with some, you know, algebra of operators. You have to look at the spectral norm of operators, but it's not something very difficult. However, maybe I give you the gist of the idea. Is that, in fact, so what the proof shows you is that S in quantum mechanics is upper bounded by the square root of 2 plus the norm of the commutator of A0, A1 times the norm of the commutator of B0, B1. And all that thing here is in the square root, okay? So now here A0, A1, B0, B1, they are the operators that describe the quantum measurements, right? And you see, it's interesting because S, you can fully analytically upper bound it by these commutators, right? So you see, the first thing to note is that if one of these commutators is 0, okay, so then its norm is 0 also, well then, in fact, sorry, I got it wrong. This has to be 4. Sorry, this has to be a 4. So in that case, so let's write it. So if A0, A1 equals 0, or B0, B1 equals 0, then S no bigger than 2. Okay, so that means that it's essentially classical. Okay, you can explain it locally. And so you see, of course, an ingredient in order to get quantum non-locality, so S strictly larger than 2, it's not only to use entanglement, but also to use measurements that do not commute. Okay, so the moral of the story is that quantum non-locality requires, well, one, it requires an entangled state, and two, it requires local measurements that do not commute. Okay, so in a sense, you can get non-locality only as the joint effect of two quantum properties, entanglement and, non-compatible measurements. So you could say the Heisenberg uncertainty principle, right? So you see, non-locality comes out of the combination of these genuine two quantum features. All right, so let me move on and finish maybe in 5 minutes with another proof of quantum non-locality, and this is what is called the GHZ paradox. Oops. So GHZ stands for Greenberger, Horn, and Zeilinger. Okay. And so this is sort of interesting because this is quantum non-locality without inequalities. Okay. So some people like to call it like this because instead of going through the derivation of an inequality as we did before with the CHSH inequality, and then prove that there is a quantum violation of this inequality, here we can go right away with just a logical paradox. Okay, so it's also an interesting example. There is a price to pay, however, for that, is that now we are going to need 3 observers. Okay, so we are going to need Alice, who will make 2 measurements that I call A0, A1, Bob, who will do B0, B1, and Charlie, who will do C0, C1. Okay, and the quantum state they use, I will denote it like this. Okay, this is the GHZ state, and that is a generalization of a Bell state. But now I have 3 qubits. Okay, so how, a Bell state is something like this: a 0, 0 plus a 1, 1. And now because I have 3, I just add 1 more. Okay, so I have a 0, 0, 0 plus a 1, 1, 1. Okay, and this is for A, B, and C. All right, and I need to close the bracket. All right, now here is the point, is that I will now tell you what the observables are. So the observables, so it's as before, right? So you see there are 2 possible measurements, and they give binary answers, which are +1, -1. Okay. Now, I just described here the quantum experiment. In this quantum experiment, the first measurement for A, B, and C, so A0, B0, C0, they are all equal to the same observable, which is sigma x. And A1, B1, and C1, they are all equal to sigma y. Okay, so that's pretty simple. No, it's symmetrical. Everything is easy. No square root 2 in the description of the measurements. Beautiful. Okay, and now the claim is that the statistics that arise from this experiment, sorry, I see that there was a comment. So you want to see the end of the previous page? Okay, I hope like this it's okay. Okay, never mind. You can still ask later if you want. So I continue here. So here I claim that the statistics arising from this experiment, you cannot explain it with local variables, and that you can see that directly, so without the need of an inequality. Okay, so that seems like a strong claim, so we want to check this, obviously, and here is the way to do it. Okay, so let me write a little table where I will write A0, B0, C0, okay? And somehow by this, I want to look at the product of these three, okay? So before I looked at the product, of AB type operators, now I want to look at the triple product of ABC, okay? Now, I need to calculate this thing for the GHZ state, okay? I could calculate the expectation value of this operator here. Now, I claim that this is a +1, okay? You see, it's the expectation value of a product of binary observables. So it has to be between +1 and -1, and here it will be +1. So let's maybe calculate that. We can do it here. So you see, this thing here is what? Well, this is so maybe let me write it like this. So the expectation value of A0, B0, C0, this is my GHZ state. Now, what is the observable that correspond to this? Sorry, I hope I can move it a bit now. So what is the observable that corresponds to this? Well, this is the sigma x tensor sigma x tensor sigma x, and all that on, whoops, GHZ. Okay? So here is just the Born rule again. Now, let me detail a little bit the calculation. So here I have a 0, 0, 0 plus a 1, 1, 1. Okay, here let me just write capital X, 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 and here I have a 0, 0, 0 plus a 1, 1, 1. Okay, so I use a bit of shorthand notations like this, but you see it immediately. So now my point is that what does XXX do on 0, 0, 0? Well, X is the flip, right? So this here gives me 1, 1, 1. Okay? The 1, 1, 1 has an overlap with this guy here. Has obviously no overlap with this one, but it has an overlap here. Okay, so I have a contribution of 1/2 already. Now let me apply the XXX to the second term here, 1, 1, 1, and this now gives me a 0, 0, 0. And this 0, 0, 0 has an overlap with this one. So I get another 1/2. Okay, so then this thing must be 1. And that one is this +1. All right, so that's good. Now I would like to do some other calculations here. I would like to have the expectation value of A0, B1, C1. Now I claim this is -1. In fact, you can see this pretty easily, because if I take again my calculation here, right? If I would have a B1 here and a C1, it means I have a sigma y here and a sigma y there. So I have a y here and a y there. And so y, remember, does almost exactly the same as x up to a factor I, okay, or minus I. Now, the idea is that it will be exactly the same as before, but we will have one factor I emerging from here and one from there. So we get an I squared, and an I squared is a -1. Okay, so you can do it in detail. I think it's in the tutorial of this week, but I hope you already get the idea here. So now I continue. I want A1 be 0, C1, and this is also -1. It's -1 because you see this is just a symmetry of that term here, right? Here I had a 0 for A and 2 1s. Here I have the 0 here, but my entire setup here is fully symmetrical by permutation of A, B, C, okay? So this has to be -1 as well. You can also check it with the calculation. And then my last one is A1, B1, C0. And for the same reason, that has 1 0 and 2 1s, so that has to be a -1. Okay? All right, so now I have everything I need. Okay? I will cut this here. Now, the point is that I have made 4 equations that capture the correlations of this experiment. And so if I somehow multiply these, okay, I will explain how I do that. Well, obviously I should have the same on the left than on the right. Okay, that seems pretty reasonable. So let me, in fact, I want to multiply the 4 equations together. But you see, on purpose, I put some space here between the A, the B's, and the C's. And it's because now I would like to do the multiplication like this. So I have a question here. Why did I not include A1, B1, C1? It's a good question. I didn't include it because I don't want it. My paradox is based on these 4 relations. Okay. So I could add more, but if already I cannot explain these 4 together, obviously I cannot explain all the rest, okay? But it's a good question. It's a bit of an artificial construction, but I do it like this because this is how it works, okay? Good. So now I multiply these things, okay? But I will multiply here column by column. This will be very handy. So you see, obviously, in this column, the product has to be +1. Okay? Why does it need to be +1? Because A0 and A1, they appear twice. Now, it doesn't matter what value I assign to A0 and to A1. Again, these things they must be +1 or -1, right? But you see, no matter how I assign these, the product will be +1 because each one comes twice. Okay. Now, it's the same thing here, right? B0 appears twice and B1 appears twice. So obviously, it doesn't matter what the values of these variables is, I should also get +1. And now, same here, I have C0 twice and C1 twice. So that should also be a +1. So if I did everything correct, well, I should have the same on the left-hand side and on the right-hand side. But if I multiply these 4 things here, obviously I get a -1. So this thing is telling me that +1 should be equal to -1. What is going on? Okay. So does someone know what is going on? Any ideas? You can make a rough tentative. Any idea is most welcome. Okay, so I guess at least you are all puzzled by by this because, well, the algebra here is sufficiently simple, so why do I get this contradiction? Well, the reason why I get this contradiction is that when I did these multiplications here, right, I assumed that these things are numbers, okay? And why did I assume that they are numbers? Well, it's because if I work in a local theory, right, if instead of having a quantum state here, I have a classical strategy, well, I can assign +1, -1 values to all of these variables, right? This is what my strategy is telling me. Now, what this thing here proves is that if I assign these variables classically by any possible strategy, well, the result here will be incompatible with what quantum mechanics predicts, okay? Because no matter how I do it, if I multiply these four things, I will have a +1, right? That is independent of my choice of strategy. And in quantum mechanics, this thing is not +1, it's exactly the opposite, it's -1. Okay, so I have really a logical contradiction. Well, now you may argue, but even in quantum mechanics, what is going on? I mean, these are just the result of the measurements, no? So why is there a contradiction here? Well, in quantum mechanics, the operators here do not commute, right? So when I do these calculations here, I'm too quick, right? I do something that is not allowed because B1 does not commute with B0. So that thing here is not just B0 squared times B1 squared. Okay. So these manipulations I can do with classical variables. Okay. So that will hold in a classical variable model or with local correlations. But in quantum mechanics, it is not true, because in quantum mechanics, the algebra is different and I get a -1. Okay? So that is the GHZ paradox. Okay? And so to summarize it here, so this paradox gives me a logical contradiction between the quantum predictions and any possible local model. Okay. So you see the difference with before is that it's not that I build a specific game with an inequality and I argue that there is a limit on the score and that quantum mechanically I get a better score. It's just really a direct logical contradiction. So something must be -1 in quantum mechanics, and I show to you that classically or with local variables, whatever you do, it has to be +1. So it's really a contradiction. Okay. However, of course, I could also translate that into an inequality if I wanted to, because I could build an inequality that would, make a linear combination between these four things here. Okay. And then I would get something that is in the spirit of the CHSH inequality. But in principle, I don't need it. I can do it directly like this. All right, so I guess it's time to come to an end. The last thing I should say probably is that beyond, all this theory here, well, you should be aware that there have been many experiments that were done on these ideas. In particular, you see the experiment suggested by Bell, or in fact by CHSH. which is this experiment here, where you have a singlet and you do these measurements here, and that should, you know, give you an experimental confirmation of this Bell inequality violation if the quantum predictions are correct. And so by the time of Bell in the 60s, no one could do that, okay, because people didn't know how to produce entanglement in the lab. But in the 70s, 80s, there were huge progress in quantum optics. And so in the early 80s, Alain Aspect and his colleagues in Paris, they could create pairs of photons which are entangled in their polarization. So it means that 0 is an H here and 1 is a V. And then they sent each of these photons to an analyzer of the polarization, so something like a polarizer if you want. And then these polarizers, they were oriented according to these 4 possibilities here, okay? And so then you can repeat this experiment many times and you can calculate the expectation values, okay? And then you calculate S. And then you check in your experiment whether S is bigger or smaller than 2, right? And so in Alain's experiment, he didn't find 2.8 because there are always some imperfections in experiments. He found something like 2.7, I think. But you see, 2.7, it's way bigger than 2. And so he concluded that this is the observation of quantum non-locality in the lab. Of course, people wanted to reproduce this experiment. By now, it has been reproduced probably 1,000 or more times, using not only photons, but atoms or other particles. And all of these experiments, they confirm this, okay? So again, you see, these experiments, what do they confirm? Well, they confirm that when you look at your data, this data cannot be explained in terms of a local theory, right? In the sense of Bell. It doesn't mean that quantum mechanics is the right theory. Of course, that would be impossible. There is no experiment that can tell you that a theory is correct. An experiment can only tell you that a theory is wrong if your theory doesn't explain what you see in this experiment, right? And this is what Alain Aspect's experiment is doing. It's saying that any physical theory that is local, according to Bell, is incompatible with what we see in this experiment, okay? So nature is maybe not necessarily quantum mechanical, but nature is certainly not a local, is certainly not described by a local theory, okay? And that is why we say that non-locality is something that is observed in nature. All right, so I guess it's a good time to conclude. Are there some further questions? I will stay online for another 2-3 minutes in case you have questions that come to your mind. Let me.
I had just a question.
Ah, perfect. Yes.
You wrote an inequality just under fundamental question. You wrote S is smaller than square root of 4 plus stuff.
This year?
Yeah, I was wondering why did you write this inequality?
So which inequality? This one?
If S is smaller or equal than square root of 4 plus the norm of the commutator of A0, A1.
Ah, okay, yes.
This inequality is not obvious to me.
No, it is not obvious. The proof, or at least the sketch of the proof, it's given in the lecture notes.
Okay.
But in fact, you can. Let me just check quickly the lecture notes. Yeah, the lecture notes essentially explain how you prove it.
I see.
Okay, but Yes, I see your point. In fact, it's something that I probably didn't explain well enough. So the point is that this inequality, it follows from this. Okay? So why does it follow from this? Well, because these things, A0 and A1, they are +1, -1 eigenvalued operators, right? Of whatever dimension, but their eigenvalues is +1, -1. And so therefore the commutator here can have a norm that is at most 2. Okay? Because the commutator is A0, A1 minus A1, A0. So the norm of this object cannot be bigger than 2. Okay? And same for this one. Now imagine it is 2. It would be 2 if you take a sigma z and a sigma x, for instance. So in this case, you have 2 times 2, that is 4. So then the point is that s is no bigger than the root of 4 plus 4. So it's the root of 8. And what is the root of 8? It is 2 times root 2. Does it make sense?
Yeah, I understand, but it's a weird way to prove this inequality, I think.
Well, if you have another way to prove this, it would be nice to see.
Mm-hmm.
You see, because this is a strong claim. This is not only telling you that for the particular experiment that I considered before, you get no more than 2 root 2. It means that for any possible quantum experiment, maybe involving infinite dimensional states or extremely large entanglement states and so on, yet you can never do better than this. Okay? And the way to do it is to prove that S is upper bounded by this quantity here. Now, indeed, in a sense, I see you're surprised. It's a little bit weird why there are these these commutators that appear. But you see, it's in fact beautiful that these commutators appear, because this immediately tells you something new. It tells you that if you want to have quantum non-locality, you need both of these guys to be non-zero. So it means you really need to have measurements that do not commute.
Right.
So it identifies another ingredient of quantum non-locality, right? It's not only the entanglement. The entanglement is necessary, but on top of that, you also need to have measurements that do not commute. Okay, but try to prove it. I mean, if you look at the lecture notes, you have to do a bit of algebra with these operators, but it's pretty simple.
Thanks.
Okay, good. Are there some other questions? All right, so I stop my broadcast here. I will probably stop the